Good evening and welcome to AP Calculus TI Office Hours. I'm your host, Curtis Brown, and I'm here with my good friends Steve Kokoska and Tom Dick, and we are just happy to be able to be here again with you this evening. I will say again, as I do often, that I so appreciate all of what you guys are doing, you teachers who are out there working in this difficult, challenging time. Getting your students ready for this new and exciting but very, very different AP exam experience that your students will be getting ready for. And any students who have joined us this evening, I thank you for your hard work too. I encourage you to keep going strong. You're almost there. How many days we've got? 6, I think, till the end. So keep it going. And before I get started, I just want to put a couple of things out there. First of all, we are monitoring the chat and the comment sections. And so if you have questions or if you have thoughts or if Steve or Tom ask a question of the audience, please feel free to put your questions and comments in the comment section. We'd love to see those and be able to respond. Secondly, just let us know where you're watching from. We'd love to know where you guys are from and who's all out there so that we can kind of cater what we're doing to help you the best that we possibly can. So Steve, I know you have some things for us, so I'll let you take it away. Thank you again for being here.
All right, thank you very much, Curtis. Delightful to be with you and Tom once again. I'm going to stop my video and I'm going to share my screen here, and I hope you can see that problem.
Looks great.
Okay, fantastic. So Tom and I distributed 2 problems through Mark Corrali's group and Brian Passwater and Tony Record, and of course through the Texas Instruments site. These are what I call sort of transition problems, possible AP Calculus exam type questions, and they contain some AB topics, of course, but also some clear BC topics. So we hope that we can get to all of those today. So I'm not going to read through this entire problem with you, but the more that I've thought about this, and as we get closer to the exam next week, I really do believe that there could indeed be a problem that is tabular in nature like this, or that is a problem that is graphical in nature. And the reason for that is because I think a problem like that does not necessarily give a student with a CAS machine any unfair advantage. So I think it's very likely that we'll see a problem like this that's graphical, or like this it's tabular. So let's take a look at this one. We're going to do some things with Riemann sums here, and that's going to lead us into some other problems. We'll get some good conceptual ideas here, I think. Suppose we have this function f, it's continuous and twice differentiable, and we have a table here that has some selected values of f of x and f prime of x. And again, I'm not going to read through all of these questions with you. I'm going to arrow down here, and I'm going to start with part A here. So the first thing I want to do is to use this table to give the best estimate for f prime of 10. Now, you're probably not going to see this word best in an AP Calculus question. I've just sort of added that word in there to remind you that if they ask you to find the estimate or an estimate for f prime of 10, they are implying they want the best possible estimate for that derivative. And what that means, at least the way that I've interpreted this, I don't think I've ever seen this in writing, but the way that I've interpreted that is you want to sandwich 10 as best you can in an interval like that, 8 to 13. Certainly there are other values of x that we could use to get an estimate for f prime, but it seems to make sense that we want to fix at 10 and get the first value to the right and the first value to the left of 10 and use that as our interval to find the average rate of change. And that's what I did here. That's the idea. I want to find f of 13 minus f of 8 divided by 13 minus 8. I don't think I did this in some of the other later parts of this problem, but I did include the table. Whoops, I'm sorry about that. I did include the table here so that you could see where I pulled those values from. And a couple of little things here in this problem. Let's just suppose that this were a 2-point problem. We're probably not going to worry about the approximation symbol. although I think that's the correct symbol to use mathematically here. Notice at this point right here, the student might earn a point because they know that that's the quotient that they need to look at, but they wouldn't get full credit yet until they actually read these values from the table. Here is a numerical answer, and I'll remind you once again that the final numerical answer does not need to be simplified, so a student could leave that. There is always that possibility that if they make that one additional step, they could make an error in simplifying and lose a point. Now, I don't know, in retrospect, I don't know whether I should have done this or not, but what I did is I included a graph just to sort of visualize this. This isn't really part of the question, but just sort of support for the idea, the concept going on in the background. Look, I don't have an algebraic expression for f. And so what I did is I just fit a polynomial through these points just so that I could visualize what was going on here. And so what I've done, of course, is I have computed the slope of this secant line going through those 2 points where x is equal to 8 and x is equal to 13. And that should be an approximation to the derivative of f at 10. So here's 10. And if I were to draw in that tangent line, you know what? That's not a bad approximation on my graph. But once again, I remind you, this is just a graph that I made up. It's not necessarily the function where I grab those table values, but I wanted to illustrate this idea, this concept.
That's a nice illustration, Steve. I appreciate that. We have a couple, you'll appreciate this. We have a couple of people, one from Canada joining us, Julia Wang, and a lot of people from all over the United States, Houston, Louisville, couple people from New Jersey, which is great. Happy to have you guys on.
Thank you. Very good. Excellent. So I'm going to try a couple here with Riemann sums. You know, in the past, we've seen a lot of problems, tabular problems, where the students have been asked to find some kind of Riemann sum, a left, right, midpoint, or trapezoidal sum. So I'm going to try a couple here, get a couple of concepts in. And once again, I'm going to maybe overstep here on this, but I'm going to try to visualize what's going on. And actually, in solving this problem, it made me really think a little bit about the trapezoidal rule in a way that I hadn't thought about before, or at least in a long time. So I want to estimate this definite integral from 2 to 17 using a left Riemann sum, right Riemann sum, and trapezoidal sum. And here's the left Riemann sum. And so what I need to do is I need to evaluate f at the left-hand endpoint of each of these subintervals. This is kind of a classic phrase here that we see. Subintervals as indicated in the table. So it doesn't really say how many subintervals to use, but that's something that the student is supposed to discern by looking at the table. So there are 4 subintervals here. I don't have the table in front of me, but I know you have the question in front of you. And so there's my formula for the left Riemann sum. I want to remind you that the student does not need to present that formula. And in fact, if the student does present a formula like that in general that is not worth any points, that is just a formula, they must apply that to the problem at hand before they can earn anything. So here in this step, I've actually applied this, and I've taken the left-hand endpoint and multiplied by the width of each of these. And I want to remind you that you have to have this product, the value of the function at the left-hand endpoint, you have to have this product generally in order to earn credit for the left Riemann sum. So I know this is getting a little messy, but going directly to here, some of our students are really good at this. And some of our students can just look at that table and very quickly write down the product, each one of these products in the left Riemann sum. It's changed a little over the years, but in general, this part here, this summation, that expression, doesn't necessarily earn credit for the left Riemann sum. What we're really looking for here is a product. In this case, 8 terms, 4 terms, 4 products, and then finally the answer. And once again, do you have to simplify this final numerical answer to 5? No, you don't. Here's a picture of what's going on, and I'm not sure if this is coming through on the screen, Curtis, but I tried to color code this so that my rectangles above the x-axis that are contributing, say, a positive value to this left Riemann sum are shaded in blue.
Hey, Steve, can I pause you just for a second? We did get a question.
Sure.
About, your notation up above. And so before you dive into the picture, which is good, I can see the colors. Quickly,
Okay.
one question. Can a student use or do just the problem without the formula? In other words, I guess, do we need to show that very first line?
That's a great question. That's an excellent question. The answer is absolutely. They do not have to show that formula. That's something extra that I put into this solution. They do not. And in general, most students go directly to here without showing any sort of formula at all. You know that we're stressing notation, but they don't have to show that.
And I would have a follow-up question to that. Given that we don't do simplify, could we just have that second row of your response and that be good enough?
And that is a superb question. And in general, that second row is worth the 2 points. That conveys the left Riemann sum, and that is a final numerical answer that does not need to be simplified. That's an excellent question. Yep.
Perfect. Jacob and I were thinking the same thing.
So here's sort of a visualization of this with my made up curve here, y equal f of x. And again, I go into each subinterval. I take the value of the function at the left-hand endpoint, and I take the area of that rectangle. The blue ones are positive. The green rectangles, I don't want to say negative area, but I subtract the area of those rectangles. So that's kind of cool. All right, well, let's do another one here. Let's do a right Riemann sum if we can. And I sort of tried the same kind of notation here and steps. This is the formula. Again, doesn't need to be shown. This second step is worth both points. It shows not only the product, but it is a final numerical answer. And in addition to that, I tried to visualize this one too. For example, in the first subinterval, the value of the function is negative, so that rectangle is below the x-axis. That contributes a negative value here to my right Riemann sum. That final answer was 21. That's kind of cool. I like picturing that. And let's try one more, and then I'll hand it over to Tom for a little technology here. Here's a trapezoidal sum. And I'm going to write a little bit on this one too, if it's okay, Curtis. I'm going to try to visualize this in kind of a couple of different ways. My picture is probably going to get a little messy. Here's the formula. Again, not necessary. Here are my 4 trapezoidal products or trapezoidal expressions as part of this giant sum. And I think the final answer there is 13. Here's how I tried to picture this. And I had to really think about this here. Let me see if I've got this correct here. I think what I want to do is first take a look at this second trapezoid and then this fourth one. Yes, let's take a look at those two first. For both of those, the value of the function at both endpoints is the same sign. So in that case, it's kind of easy for me to see, well, I have a trapezoid here. It is all below the x-axis. That contributes a negative value to the sum. There it is. Over here in this interval, both of the values at the endpoints are positive. So I can see my trapezoid. That contributes a positive value. Beautiful. Okay, so what's going on at one of these others, where one of the values at one endpoint is positive and one is negative? Well, here's what I'm going to try to scribble a little bit, all right? Now, I've sort of drawn in this region as a triangle, and here's how I thought about this, okay? Here, I'm going to try to show you a couple of ways, and I know Tom will help me with this. If I take a look at this trapezoidal, or this product here, the sort of area of a trapezoid, it is 1/2 7 plus a -1, there are the values at the two endpoints, times the length of the subinterval, which is really the height of the trapezoid. Now, this doesn't really make sense where one of them is negative. And so here's what I did. I looked at this as 1/2 times a 6 times a 3, and I thought of that as the area of a triangle. it's positive. It's above the x-axis. And so what I did is I drew in a triangle here with base 3, with height 6. And again, because this product was positive, it contributes a positive value to this giant sum. So that's why I drew it in blue, and that's why I drew it above the x-axis. But there are some other ways to look at this, and my picture is going to get a little messy. I'm going to try something a little fancy here, Curtis. I'm going to erase that and try to draw in a little more.
Okay. Before you do, can I ask a question?
Sure, shoot.
I have a question from Will Atkinson. Says that do we need to show the math for finding the lengths of those intervals each time?
So the lengths, these right here, I think is the question. Yep. No, I would say no, you don't have to show that. I did it out in gory detail so you could see where everything's coming from. But certainly the student can get those lengths easily in their head. I think the point is that we'd have to see evidence of the trapezoidal rule. What are we looking for there? Generally, we're looking for a height, a sum, and the 1/2. Yes, could they factor out the 1/2 out of everything? Absolutely. But again, I would say we're looking for a product. We're looking for 4 products there.
Okay. I've got another question right up against that trapezoidal rule, and that I'm just going to read it so I say it correctly. If this question was given on an AP exam, is it enough to say that since the trapezoidal approximation is the average of the left and right approximation, L plus R divided by 2 gives you your answer?
That is a great question, and the answer to that is yes. So if the question on the AP exam were something like find the left Riemann sum, find the right Riemann sum, and now find the trapezoidal sum, absolutely you could do that. If the question simply said find a trapezoidal sum with nothing else before it, the student could solve it this way, that's on this page, or if they really wanted to, if they find it easier, they could find the left Riemann sum first, then the right, and then take the average.
Sure. Okay.
Okay.
Good.
So here's another way to look at this. I'm sorry, Curtis. Was there another question?
No, there's not. Just no. I think we're good.
Okay. So here's another way to look at this. One way to think about this is that this value 9 is sort of the average of the area of 2 rectangles. So if I take a look at one rectangle here with width 3 and height 1 or -1, and another one over here with height 7 and width 3, I'm sorry about that. There is an average of those 2 sort of areas, and it is a rectangle with height 3 and width 3. I probably should have done that in different colors, but that is another way to sort of picture this. And there are probably others. I think the point is, one of the reasons that I did this problem, the point is that sometimes when students see values here at the left and the right-hand endpoint that are of different signs, sometimes they panic in using this trapezoidal rule because you can't quite picture that trapezoid. But if you just follow the formula, follow the prescriptive notation and formula, it leads to the right answer. Now, one question that I sort of took out of here, but is I think sort of an interesting one, and often the College Board asks, is which of these 3 estimates do you think is the best and why? Explain your reasoning or justify your answer. And so with that, I'm going to turn it over to Tom for a little technology, and then we'll come back and look at some of these other questions. So Tom, what I'm going to try to do. Tom jumps in,
Steve, I got one more question for you.
Yes, go ahead.
So that is, if this were asked as a midpoint sum, what might that look like? Or is that where you're headed in just a moment?
I'm not headed there. If this were asked as a midpoint sum, it would have to be asked with a different number of subintervals.
Agreed.
So probably we could ask a question like, I'm just thinking about quickly looking at my table. I think we could ask for a midpoint sum based on 2 intervals and equal to 2.
You have 5 points, right?
I have 5 points. So we could do
so
2
2
intervals.
would be about the best you could do.
Yeah, would be the best we could do. That is correct. So that's a really good question. I mean, you might you know, that would force students to think a little bit about how do you really use the midpoint sum. It is a different number of subintervals than the left and the right. Good question.
Yeah.
Okay.
Tom, you ready?
Yeah, I don't know.
Okay,
Is my screen showing?
It's not. You're going to have to do the share and then remember the little blue button that says share also. You have to do
Okay. So let's see. And that button, I did share screen at the bottom, and I also need to do.
You need to choose the content and then choose the share button.
Okay. All right, I might need a little bit of help here. So we're there. I see share screen. I've
So
pressed
choose
that.
what, when you click that, you're going to get an option and then choose whatever you want to share. And
Okay.
then down in the bottom of that window that pops up, there'll be a blue button that says share, and click that one.
Oh, I see.
There we go.
Okay, so we're on board. Okay, sorry for the little hitch there. So I just want to take a little bit of an opportunity. I've got the TI-84 Plus emulator here. And this was a tabular STEM kind of AP questions. These are pretty popular. And I was just going to show folks how you can use the stat plot for such questions to get a nice visual look at what you're dealing with. So what I've done is if you do a if you do stat, let me try that again, stat edit, you'll get into this list editor, which looks kind of like a little spreadsheet. And I'm just, we've got these pre-named lists, L1, L2, and so forth. I'm just going to use those as is to enter the values from the table that we were given in Steve's example problem. So in L1, I'm going to enter the X values, which were 2, 5, 8, 13, and 17. And then I'm going to go over to list 2, L2, and enter the f of x values, which were 7, minus 1, minus 5, 3, and 6. So quickly enter those. And now, I mean, with graphing calculators, we spend most of our time with y equals and the graphing functions, but here I'm actually going to use a stat plot. So I'll go to my stat plot menu, which is the second shift of y equals. I'll go ahead and do plot 1 here. I'm going to turn that on. And I'm going to change, well, the type here, it's actually on the one I want. You can have a dot plot, but I actually want this kind of connected 9-segment plot. And I need to, I'll make my X list. My X values were in list 1. So I'll make list 1 there. And my Y values will be list 2. And let me try a zoom, let's see, zoom stat. Let's try that, see what we get. And here we've got this nice, it's basically a piecewise linear approximation given just the values in the table. So a couple of things I just wanted to point out here is just entering the values in the table and plotting that as a scatter plot or a stat plot. It's kind of really nice for both parts A and parts B of this problem that Steve has presented. So for example, I think that first problem was to find an approximation for f prime of 10. And the approximation that Steve came up with is actually just the slope of this line segment that connects the value at 8, -5 to 13, 2. I think he got 8/5 out of that, but that's just the slope of that segment that connects those up. Also, Steve talked at length about the trapezoidal rule, trying to kind of think about that in terms of areas of trapezoids and triangles. And certainly if you have 2 points in the table that are both below two adjacent points that are both below or both above the x-axis, you can visualize a trapezoid. But in general, you can think of this as just integrating a piecewise linear function. So we have a triangle here from x equal 2 over to where this first crosses. Then we have a little triangle here whose area would contribute negatively. Then we have an area of a trapezoid that contributes negatively, an area of a triangle here that contributes negatively, and an area of a triangle that contributes positively. And then finally over here, a final trapezoidal contribution. So another way to think of the trapezoidal rule is you're actually integrating a piecewise linear approximation based on your table. So that stat plot, it's the values that we were given here were pretty nice. It's actually pretty quick to enter those in, and then we've got this nice visual picture. Steve, I don't know if you want me to take a crack at your question or not, but
Go right ahead.
well, in general, Steve drew in a nice curve that went through all these points, but I can sure think of a whole lot of other curves that could go through all these points, including, well, I don't think this one would be good because it's not going to be differentiable, but there's a lot of smooth curves that would go through these points where I could make any of those three estimates better than the other two. So the answer to the question is you can't tell based on just the table value alone.
You can't tell. Yep. Very good.
All right. Well, that's all
All
I've
right.
got. I'm going to turn it back over
All
to
right.
Steve. So I'll stop the share here.
All right. Here we go. Can you see part C?
Yep.
I can see it.
Okay. All right. Fantastic. All right. So here's a couple more that go along with this general function ff prime, I think, in there that we have at the very beginning of this. It says, show there's a value of C in this interval so that f prime of C is equal to 1/2, or show that no such value exists. Well, okay, we've seen several questions like this in past years. And this is screaming out mean value theorem. I think we said at the very beginning of this problem, I'm going to sneak a peek back here. We said that f is continuous and twice differentiable, but I'm going to underline this here again. Remember here to impress upon your students that whenever they invoke a theorem like the mean value theorem, they must make sure that the assumptions are true, that they state the assumptions. Now look, in this particular problem, we already told the student that the function was continuous over this entire interval and differentiable. But in general, it's not necessarily given. The student must deduce that and conclude that in some way from information given. Make sure that they state the assumptions in order to invoke a certain theorem. Now, okay, you do have to root around a little bit here, and I found an interval 5 to 13. So if I take a look at this ratio, that average rate of change, I do indeed get 1/2. And so by the mean value theorem, there must be a value of C in that interval 5 to 13. So certainly in interval 3 to 17, so that f prime of C is equal to 1/2. That's kind of a standard 2-point question. And again, if we see a tabular question on the exam next week, I wouldn't be surprised to see something like this. Now, there is an alternate solution here that I think students have been using in the past, recent past. It turns out that we said in this problem that f was twice differentiable. So that means that f prime is differentiable, and that means that f prime is continuous. And so since I have some values for f prime, I think I can use the intermediate value theorem. Now, again, you have this problem in front of you. I'm going to arrow down a little bit. Don't look at that graph yet. But I think if I look at my chart, my table of values, I think I see that f prime of 5 is equal to 0, which is, of course, less than 1/2, which is less than 2, which is less than f prime of 8. And so because f prime is continuous on this interval 5 to 8, by the intermediate value theorem, there must be some value C in between so that f prime of C is equal to 1/2. That's kind of a cool application, and that's an alternate way to solve this problem. Now, this graph...
Go ahead, Tom.
Sorry, Steve. I think you probably want an equal sign on that last inequality.
That is equal. It's very difficult to see.
Okay.
Hey, Steve, I do have two questions that popped in. One,
Sure.
and that was, if the function is continuous and differentiable over the whole interval, which we've stated, can you use the whole interval when using the mean value theorem on a smaller subsection like the interval in part C?
If I understand the question correctly, if the function is continuous over the whole interval, it's continuous on any subinterval. If it's differentiable over the whole interval or the open interval, it's differentiable on any subinterval.
Right.
So yes.
So
Absolutely.
the answer then would be yes, you could use the whole interval when using the mean value theorem on a smaller section.
I'm not quite sure what that's saying. If it were the case that in order to show that there were a C like this in that interval, that I had to use this interval rather than this one, I could say that F is continuous on the closed interval, 2 to 17, differentiable on the open interval 2 to 17. So what I've done is I've used the mean value theorem on the interval 5 to 17 here, but if need be, in order to find a ratio, a quotient where I get 1/2, I could use the whole interval if that's the answer to the question.
I think that's the answer to the question.
Okay.
That's the answer to the question. Secondly, is there a shortcut to determine we can use to determine whether or not the mean value theorem is applicable, or should we just look at the points and use trial and error?
Yeah, that's a good question. I don't know of any shortcut offhand. I think trial and error, pattern recognition, good vision. I don't think there's a shortcut there. I mean, sure, if I had technology available, I could probably come up with some way to look at all of these possible quotients, but look, it's just trial and error. Theoretically,
Okay.
I mean, the College Board isn't going to give you a table here with 10 values or 10 subintervals and expect you to look at all possible. It's going to be, I hope, pretty obvious. Okay.
Sure. Okay.
And down at the bottom here, this picture does not do justice to this intermediate value theorem alternate solution. And the reason is because, again, I made up this function. As Tom mentioned a minute ago, there are lots of functions, nice smooth curves that could go through these five points. But at least for this one, here's a secant line through those 2 points. And I found a value, I think, in between 5 and 13, where the slope of the tangent line is indeed parallel, or the same, excuse me, as the slope of that secant line. If you take a look at this argument right here, it sure looks like there should be a value between 5 and 8, and that doesn't really hold true, I think, over here in my picture. But again, that's because I made up this function f. Cool. Let's shift gears a little bit, look at a couple of other theorems here, maybe do a little bit more analytic stuff. I think there's some good concepts going on in the background here, and also a little bit with notation. On part D, we're asked to find the value of 5 to 13 of f prime of x. Again, I think this is a nice problem because it's not necessarily what I would call algebraic. I don't have an analytic expression for f prime, yet this forces the student to use the fundamental theorem of calculus. Here I have an antiderivative of f prime, which is f. In order to evaluate this, I evaluate f at the upper bound 13, the lower bound 5. I have to go to the table to find those values. Again, there's a final numerical answer, but I simplified that to get an answer of 4. So again, I think in a problem like this, I think that a student does not have any sort of advantage with some super technology here. I think that's a good one. In part E, there it is. In part E, find an equation of the tangent line to the graph of f at x equal 8. Very common sort of a question. From looking at the table, I have a point. From looking at the table, I have the slope. I need to put these two together. So let's see, there's y minus y1 is equal to the slope times x minus x1, and there's a couple of little things in here, some subtle things in here. Here is an equation of that tangent line. The student can leave that equation like that and indeed get full credit. They could indeed write it like this if they wanted to, y all alone on one side of the equation. There is, of course, this possibility of going from this step to this step that the student might make an error and therefore lose a point. So again, a test-taking strategy is to, well, leave it in this form. One common error that we often see in problems like this is a student will present the equation of the tangent line like this: y plus 5 over x minus 8 is equal to 2. I'm sorry, Curtis, I apologize. I haven't asked many questions here, but here's a good one. Why is that incorrect? That is not the equation of that tangent line and would not earn credit. And why don't we leave that open for a little bit and maybe we'll get an answer to that one, okay? So that does not get credit, and you might think a little bit about why and make sure that I answer that before we leave this problem, okay? All right, here we go.
All right.
F.
I think I know why, but I want to hear.
Okay. All right, this one, for F and G, we know a little bit more information here. Suppose we also know that F double prime of 5 is 4, F triple prime of 5 is minus 6. And so one question is, does F have a local min, local max, or neither at x equal to 5? And explain your reasoning. So again, I did not print the table again, repeat the table on this part, but the first thing I did was look at F prime of 5, and that is indeed 0. So in my mind, that says that x equal to 5 is a candidate for a local min max. It is a candidate. I don't know if it's either yet. I took a look at F double prime of 5. I'm given that here. That's 4. That means that the graph of F is concave up at x equal 5. So let's see, what does that mean? There's a local minimum. There's a local minimum here at x equal 5. That's kind of cool. That's a neat application of a couple of theorems, a couple of ideas going on in the background. Again, I've tested some important ideas, I think concepts in a tabular way without giving anyone, I think, an advantage. And finally, let's get some BC ideas in here. This says find the third degree Taylor polynomial for f at x equal 5. And very often we're asked to use it to approximate the value of the function. So here we go. I'm going to find t sub 3 of x. This is the general formula. I know I'm going to get this question. Does the student have to write that general formula? No, of course not, but I did so you could see where everything's coming from. I grabbed all of these values, f double prime of 5. I grabbed these two from the table. These two right here were given to me extra in this part of the problem. Kind of a neat thing here is that f prime of 5 is 0, so that first degree term drops out. And I did a little bit of simplification. We had some nice cancellation there, and there's my third degree Taylor polynomial. Now, there's a subtle point down here in finding this approximation. We want to use this Taylor polynomial to approximate the value of f of 4. So, of course, what we would do is take this value of this expression for t sub 3, and we would plug in an x equal 4. This is an approximation symbol here. And generally in these series questions, these Taylor approximation, Taylor polynomial questions, that's where we get a little picky, testy about approximation symbols and equal signs. Now, this one here is in a gray area for me. If a student wrote an equal sign there, I'm going to say probably. Don't quote me on that for next week, but they probably would not get a point taken off. But it is, clearly, should be an approximation symbol. But while we're here, this is the one where students generally lose points. If they write something like that, where the function f is equal to its third degree Taylor polynomial, that's definitely incorrect mathematics, and that's sort of across the line. That's at a place where we generally take off a point somewhere in the problem. So for your BC students, a test-taking strategy, just have to be very careful with those equal signs and with those approximation symbols. I guess the overall point is don't equate any of your Taylor polynomials here finite degree Taylor polynomials to that function f of x.
That's a good
Cool.
point, Steve. So I have a couple of questions here that have popped up. One that I'm not sure about. I'm not even sure how it would turn up, but is a factorial like 3 factorial considered a final numerical answer? So if I
Yes.
3 factorial, that is a final numerical answer, correct?
Yes, it is. Yep.
Okay. I thought.
Yep. And while we're here, before you get to the next one, not in this problem, but even something like this, sine of pi over 4, that's a final numerical answer.
Sure.
Okay. We had one, I believe, last year. Tom helped me on this, but I think it was something like arctan of 0, right? That's a final numerical answer.
Yeah, I don't know if that was exactly it, but certainly anything like that is considered a perfectly valid numerical answer.
Okay, sorry, Curtis, go ahead.
Okay, I had another question. Not sure what it's really pertaining to, so we may need to ask for clarification, and that is, can you please explain f again? Is f prime doing anything here? I'm not sure. I think that might be pertaining to the question you had on part.
Previous one?
Mm-hmm.
Perhaps the previous one?
Mm-hmm.
Well, in this one, in part F, we know that 5 is a candidate for a local max or a local min because f prime of 5 is equal to 0. And I got that value from looking at the table of values that was given to me in the statement of the problem. And also we're told that f double prime of 5 is equal to 4. So that means the graph of f is concave up at x equal 5. So for
Right.
concavity, a function can be concave up at a point, at a value. That means that the graph of f is like an umbrella or a cup at that point. So the tangent line is below it. And so that means that f has to be a local minimum.
Right. Right.
Okay.
Okay, I've got that. I think that clarifies. Perfect. I have one question related to the Taylor polynomials here. So
Okay.
that is, could you say f of 4 is approximately equal to t of 4, which equals the polynomial with the plugged in values?
Okay, so if I understood that question correctly, you can certainly say this, okay? That's a correct statement. I don't know if that would get you any points, but that is a correct statement. This is not a final numerical answer.
Right.
So I believe you would have to take that 4 and actually plug it in. So 1 plus, okay, whatever it was, minus 1, I guess, 2 times 4 minus 5 squared minus 4 minus 5 cubed. That's a final numerical answer.
Sure. I think that's what Zach was getting at here on his question. So good, good on you on that one. So one thing, so you asked a question just a minute ago about why the tangent, why that wasn't the equation of the tangent being shown that way that you had up there on part, I guess that was part E, where you had that question. And we had a large number of people who mentioned the domain restriction on your
excellent
there, which
excellent.
was headed as well. So fabulous.
Very good. Excellent. Yep, that's a subtle point, but this equation, this describes something very different from that, right? Because of the domain. A function is defined not only by its, like, say, algebraic components, but also by its domain. Very good. Excellent. All right, I'm going to try to switch here a little bit, if it's okay with you, Curtis. We'll go to this next one. I don't know how far we'll get. You interrupt me whenever you need to. This one is more of a BC question. Here, again, we have a table of values. You'll notice we have f prime, f double prime, holy Toledo, f triple prime, and the fourth derivative evaluated at a couple places. And again, I won't read through all of this with you, but notice that we say here that f prime is decreasing on this interval 0 to 2. So let's see if we can take a look at some of these. So the first one is, right, the first degree Taylor polynomial for f about x equal 1, and we're going to use this expression. This is similar to what we did a minute ago. but this is a very common sort of question in a BC problem. Is this approximation greater or less than f of 1.1, the actual value? So, all right, here is the first degree Taylor polynomial, which of course is the tangent line approximation. I got these two values by reading off the table. I want to approximate f. I take 1.1 and plug it in. I did a little bit of arithmetic here, and I think I got a 6.5. This is a little subtle. We got to think a little bit about this. We know that f prime, let's see. It says in the problem that f prime is decreasing on the interval 0 to 2. Now, I suppose there are several ways to look at this, but that means that f is concave down, okay? So that means f is concave down. So I'm going to draw a quick picture here. This is the way that I kind of see this, all right? Here's 1. I know that f prime is decreasing on this interval 0 to 2. So that means f is concave down on that interval. So that means when I draw the tangent line, at least in the neighborhood there, that tangent line is above the curve. So that means that when I take a look at my t of 1.1, it must be above, it must be greater than the actual value of the function. Now, we've seen some questions like this on the AP exam in the past. Student doesn't have to draw a picture, but in general, they do have to refer in some way to concavity to know whether or not that tangent line is above or below the curve. And often there's some extra information given in the problem that will allow the student to deduce whether or not that function is concave up or concave down. And the important thing here, I think, to remember is on an interval. You can't just say at a point. You can't just say at 1, even though that might be true. We need to know that it is on this interval, actually, that includes 1.1 in this case. So that's kind of a neat question. There's a lot of little things going on there, but I thought that was a good one to get us going. Here's part B here. This is a quick one. And one of the reasons I put this in here is because, you know, sometimes the College Board, sometimes that test development committee throws us a little curve, and they did something like this on a question within the past couple of years. Does f have a critical number at x equals 0? Why or why not? Well, think back here a little bit. What is the definition of a critical number? I added that in there. A student wouldn't necessarily have to do that, but I put that in there for my own benefit. A critical number of a function is a number in the domain so that f prime of c is equal to 0 or f prime of c doesn't exist. Well, I took a quick look at the table. I saw that f prime of 0 is 7, and I know immediately that f does not have a critical number at x equals 0. So this kind of a question was asked in the following context. A couple of years ago, the question was something like, does f have a local max, local min, or neither at x equals 0? And students did not check f prime of 0. They immediately went to look at f double prime and determined whether that was positive or negative to use the idea of concavity, the second derivative test, telling us whether or not we had a local max or a local min. But in fact, the answer was neither, because it wasn't even a critical number. So this is, I don't want to say it's a subtle point, but don't forget the little things here. I'm not saying that they're going to trick us with only 2 problems, but that kind of a question came up a couple of years ago.
Okay, Steve, before you move on, I think I have 2 questions. One might be related to part A. Apologize, I was trying to take care of getting the questions into the chat here. Is it acceptable to just say that f double prime of 1.1 will be less than 0, so the approximation is an overestimate? Or is the word concave required as a part of the number?
All right, I would say that in a problem like this, you have to state that f is concave down on an interval containing 1.1.
Okay.
You cannot just say that f is concave down at a single point.
Sure.
Okay, and I don't think there's anything, in here in this problem that we gave. We did not evaluate f prime or f double prime at 1.1 And so you've got to use some other information here to come up with an interval so that you know that this tangent line is above that graph over that interval.
Good. Thank you.
Okay.
Answers that.
All right, let's take a look at C. Let's get to a BC question. Write the third degree Taylor polynomial for f about x equals 0. Yes, you're right. This is a Maclaurin series, but sometimes on the AP exam it's stated like this. Not to trick anyone, this is a Taylor polynomial, but it has a special name. Again, I wrote in the formula here, not necessarily, but there it is. Very straightforward, easy, sort of a prescriptive kind of problem for your students to pick up some points. I know what the equation is. I went to the table here, read all the values off the table. This is a final answer right here. It does not have to be simplified, but of course I did here. I wasn't working under the pressure of a high stakes exam. This line right here would be acceptable. If you happen to, if the students write down the formula like this, in general, that's not worth much, if anything, because it is formulaic. It's not applied to our particular problem. D is kind of a standard problem, a question that we've seen in a couple of years in a row here. It says, write the first three non-zero terms in the Maclaurin series for y equal f of x times e to the x. Well, a couple of things. We now realize that we have the Maclaurin series for f of x in part C. And the student has to know what the Maclaurin series is for e to the x. Now, look, in the past, you know, DC6 is usually the series problem. This is not open book, open notes, open calculator. And so the students have to know what the Maclaurin series is for e to the x. Now they've got their open book and open notes, and so they can always look this up. But here's the type of thing that they need to do. I wrote down the third degree Maclaurin series for f of x, and I wrote down the first few terms of the Maclaurin series for e to the x. Now this says I want the first three non-zero terms in this Maclaurin series, so I'm not exactly sure how many terms I need, but I figured 3 was enough. And so what I did is I took 9 and I multiplied times the first 3 there, the 7x and this 5 halves x minus 5 halves x. That's what I did here. And I collected some terms and I realized, you know what? I have enough. I can see my first 3 non-zero terms. I know, Curtis, a question that's coming is, can you leave it something like this? And the answer to that is, in general, no, you can't. We really need to see those first 3 non-zero terms collected. I don't want to use the word simplified, but we need to see those 3 non-zero terms explicitly. So that's kind of cool. And you know, to me at least, there's some neat conceptual ideas going on in the background there, that you can indeed create this new Maclaurin series from some old ones. You can get a new Maclaurin series for a new function from these old ones. That's kind of cool.
That is nice. That's a
All
good.
right.
So Steve, can I jump in there for just a second?
Please. Sorry, Tom, go ahead.
You know, it was just occurring to me an alternative that some students might use, and it would be perfectly okay, would be to take your expression y equals f of x times e to the x and actually evaluate it at 0, take the derivative, evaluate that at 0, take the second derivative, but you don't even need to do that twice. You would get this kind of double product rule going, but and then put together the Maclaurin, the first 3 non-zero terms that way. Should get the same thing for sure. Yeah.
Yeah, that's an excellent point. And you know what? We should ask our teachers out there to have their students do it that way to make sure they get the same answer. That's an excellent exercise, Tom. Excellent idea.
That's a really good idea. Hold the boat.
Hold sorry. Go ahead.
Got a question that came in, and I think it's a very good question. Considering what we know for this year's exam, would this part B fall into the series manipulation of non-tested topics for 2020, or do you think that this could be potentially fair game?
You know, it probably falls into a gray area. It probably falls into that area of manipulation of series. But you know, the truth is, this probably isn't that difficult. I mean, and even if you haven't covered this in class, it's pretty intuitive about what you do. But I don't know. I guess if the push comes to shove, I don't know if you'll see one like this on the exam this year. I agree.
Right. Good. Good. Final thing here. Do we need to show the multiplication step, or could you just say f of x times e to the x is approximately, and then the three non-zero terms?
If you're good enough to go right from there to there, more power to you. Yeah, I would say you don't necessarily have to see that multiplication step, but on the other hand, there's probably some partial credit in here.
Yeah.
And so without seeing that step, you have a good opportunity to lose that or not earn it.
I know I would. I'd have a significant opportunity to
I don't believe that.
get all of those points.
All right,
lose all
I
of those
want to
points.
say, yeah, I know you're not going to let me, but I'm going to try to take a look at these. I really like these last couple. I think these are good questions too, testing some good topics here. This one is find the definite integral from 0 to 1 of x f double prime of x. This one is integration by parts. How do you know how to solve this one? A little bit of pattern recognition, a little bit of calculus vision. I kind of look at that and see x times, you know, a transcendental function. That's not true, but that's what I'm seeing with my pattern recognition. And so that screams out to me that I want to use integration by parts. So the logical thing to do here, if you've done enough of these in class, is to let u be equal to x, dv, what's left over. This is the way that I do these. I try to write this out very explicitly. There's my expression for du. There's my v, the integral of dv. There is n antiderivative. This is the way I write this notationally. This is perfectly acceptable in this step right here. It is understood that I'm going to evaluate that entire expression at the upper bound and the lower bound. I know that there are a lot of people who, when they look at a problem like this, will come off to the side and first find this general antiderivative, x f double prime of x dx. They will solve this with integration by parts without any limits of integration, and then go directly, I believe, back to this step. And that's fine. I'm sort of combining everything in one here. Here's my integration by parts step. I still need to integrate this, and I can do that. There is n antiderivative. And again, this is kind of nice. No advantage to a person with a CAS machine. I do have to go to the table and look up some values for f prime of 1 and f of 1, f prime of 0, f of 0. And I did a little bit of simplification to arrive at a nice, easy 8. And again, here is a final numerical answer that does not need to be simplified. So this is a nice problem. It forces the student to use integration by parts. There is some notation issues. There are some notation issues here. The student has to be careful about this, where the 0 and 1 goes. They shouldn't just disappear and then reappear at the end. Be careful of those.
So Steve, I have
another
two
one.
questions that have kind of popped in.
Okay.
Couple of things. First of all, I have a shout out to make sure that I do so I don't forget it, which is for Gian Baratella. That teacher's gotten all of their students to attend this evening. So we do have quite a few students on, and I think that's where the bulk of your questions are coming from, which is great. Love that the students are on asking questions. This is what we intend, that people are getting the information they want, and that they're getting the help that they want, especially, you know, just having your availability here, which is awesome. So thank you for that. I do have a question about the solutions. Are we going to post those solutions? We posted the questions. Are we going to post the solutions to these any place?
Well, that's your choice. I will certainly give you the PDF files like I did with the other ones. That's your choice. If you want to put them somewhere,
Fabulous.
That's fine with me. Okay.
I will make sure that those get posted someplace. Jennifer, we got you taken care of.
Okay.
I will hold off to the end, though.
Thanks, Curtis. All right, here's another good one. Find the definite integral from 1 to 2 of f of x, f prime of x. Allison, I know you're giving me the 0 seconds, 0 minutes, but just let me finish these last two. This is a nice one, too. And this is actually a substitution problem, I believe. And again, I've done everything out in kind of gory detail here, where u is equal to f of x and du is what's left over, f prime of x dx. I'm going to show you a couple of notational things here very quickly. Here I've started with a problem in the x world, and here I am bringing this problem into the u world. If I bring the integrand into the u world, I'll remind you again that you got to drag along the bounds. I know somebody's going to ask, look, can you write up here x equal 2 and x equal 1? We may have talked about this in a previous office hours. Yes, you can, but why would you want to? This step right here is, in my opinion, and I'm sure on the AP exam, if you see something like this is okay. This is an intermediate step. This is my bridge. I'm halfway to the U world. In this next step, I'm going to cancel out those two expressions, and I'm going to be left with an expression in all of U. Very simple integration, basic anti-differentiation rules. I plug in my upper bound and my lower bound. I ended up with a minus 11/2. Here's a follow-up question to this. Try to generalize this a little bit. I like this question. I've given this one on a couple of my calculus exams. What's the integral from a to b of f of x, f prime of x dx? That's kind of a neat problem. So there's some notation issues there. That's a substitution problem, not necessarily just a BC question. And let's end this one with another substitution and a couple of properties of integrals. There's an awful lot written on this page. There's some nice concepts going on here. Here's what I see when I look at this definite integral problem. Boy, we've got to use lots of ideas here. The first thing I see is I'm going to split this up into two separate definite integrals. That's a property of definite integrals. And the next thing I see is, well, when I split it up here and here, I think I see a U-substitution. If I let U be equal to the argument of f double prime, the derivative of that is just a constant 2. And so I can handle that when I bring everything into the U world. Constants aren't an issue. So, all right, there's my substitution for that second definite integral. There's du. Again, I need to bring the values in the x world into the u world. There are my two values in u. So this is kind of cool because this first integral stays over here in x's. The second integral is in u's with the correct bounds. Lots of notational issues going on here. Basic anti-differentiation rule right there. F prime of u is an antiderivative. This is easy to get. I plug in the upper bound and the lower bound. I had to work a little to make this come out. These values I can look up on the original table, and I do a little bit of simplification for a minus 9/2. Boy, there's a lot of cool stuff going on in there. We saw a problem, something like this, I think it was last year or the year before, where there was a sum as an integrand, and I think it was an f prime in the integrand, and of course the students had to go to a table to get some answers. So this is a kind of a nice problem and very similar, analogous to one that we've seen recently. All right, Curtis, that's all I've got, unless you've got a couple of questions.
So I haven't seen any new questions related to this come in. Just a few more call outs for teachers, and that's awesome. I do have one question that came in from one of the students, and that was, when's part 5? So I will make note that we have 3 other of these same kind of office hours deals on our YouTube channel that Steve and Tom have done related to calculus, and so this is the 4th one. And as of right now, until maybe just shortly after we get off of here, this is the last one prior to the AP exam this year. It might be tight to fit another one in before next Tuesday, but we'll chat about this and keep going. We'll let you know if we decide to do another part. So we hope everybody has a good luck and gets good night's rest before next Tuesday. That's always an important thing. Make sure you sleep super well, study hard, and go back and watch a couple more of these YouTube office hours. I think you'll get some good key tips from these guys before that. So anyway, really enjoyed tonight's session, Steve. You know, back when we were first discussing doing these, this is exactly what we envisioned, having students on here asking questions, teachers on here asking and answering questions. So Steve, Tom, this has been exactly what we thought it was supposed to be. So thank you so much for giving us your time and being on here with us this evening. So before we go, maybe some final tips and video like on Apri Central YouTube channel. Maybe we can come together. We'll think of something and maybe we can post a video rather than a live chat or something. We'll think about it and we'll let you know what we decide to do. So thank you guys so very much for hanging out with us this evening. Thank you for giving us your time. I guess we'll sign off with that. So thank you very much. Good night.